let me start today's presentation. So my name is Minden. I'm a PhD candidate in the University of Michigan. And it's my honor here to, on behalf of our team, to present the research review of our CCAT project. I'm under supervision of Professor Carol Menassa and Professor Vinny Kamat. And we work with our colleague from Clemson University, Aaron Glang and Yijin Zhao. And they are co-supervised by Professor Dali and Professor Julian Brinkley. The topic for our today's project is can physiological sensing indicative driver takeover ability in level 3 automation. And in today's presentation, I'm going to give you some background about our project, and I'm going to introduce some detail about what we have done and what our future plan is regarding this project. So let me start with the outline of today's presentation. And at first, I'm going to give you some background and the motivation of this project, meaning why we do this project and why this project is important. And then I will go to the objective of our project and also the objective of today's presentation. And to achieve those objectives, I will raise up some research questions we need to answer and followed by how we design the experiment. And I will show you some detail about the experimental design and the data collection. And we also will show you some preliminary observation of our collected data, meaning some distribution of the raw data. And then based on those observations, I'm going to introduce what we are going to do in the future based on our preliminary observation of those data. So let me start with some background of the project. So why the autonomous vehicle is important? Because according to some report, by 2045, about half of the new vehicles are expected to be autonomous. And the autonomous vehicle can potentially reduce the driver stress and fatigue and the traffic congestion. And it may also be able to improve the safety, mobility, and the economic efficiency. And for a current level of autonomy in the commercial market, for example, the Tesla and the Cadillac, they mainly belong to level 2, which means it's partial automation. And at this level, level 2, the driver must always observe the roadway and they need to resume full control immediately when the system reaches limit. But our target is on one level higher, which is level 3. And in level 3, the driver is allowed to perform some secondary tasks, meaning they don't need to always observe the road. They can play their phone and they may be able to watch some movie. And once they are required to take over, they can get some alert and do that. But at level 3, although the driver is allowed to be distracted from the secondary task, they still need to take over in some emergencies. So the failure of takeover will also result in the fatal incidents. For example, if you see the flash here, you can see it's a fatal instance happened in Taiwan in 2020, and the car was test mode. The car just failed to stop from overturned commercial track, and when it was hit, the autopilot was engaged. So it means the takeover, the in-time takeover is very important. Otherwise, it will cause some severe result. And in general, for the level 3 autonomous driving, what we want to achieve is eye on but mind off, which means the vehicle can manage all the safety critical functions under certain conditions without the driver's supervision. However, the driver are required to take over if a request is initiated. But how do we know when the request is needed, and how can we know when the driver is ready to take over the car? So it becomes very important for us to know or to predict the driver takeover performance. So to do that, we did some literature for previous study, and there are some high-level influential factors of takeover performance in level 3 automation. For example, some studies highlight the driver characteristic on charging autonomous vehicle, and some studies use the galvanic skin conductance, meaning GSR, and eye movement for the takeover performance prediction. And some other studies also investigate the effect of technical tasks, of the alert, and on the traffic density on the takeover performance. However, even some research has been done in previous study, there's still some research gap we need to investigate. For example, for the previous research, the lack of knowledge of how the driver's mental status, which can affect the effectiveness of the takeover, meaning they can do some initial prediction, but the mechanism behind the brain of the driver is still unclear. And they were able to achieve personalized prediction of the driver takeover performance. Because people may differ a lot from each other, meaning they may have different behavior, they may be used to different kind of alert. It means a personalized prediction of the driver takeover performance might be also important, might be more efficient. And they were able to adaptively alert the driver. For example, some driver may be more sensitive to the sound, some of others may be more sensitive to the visual alert. So we may adopt those findings to the design of the alert. And here we have some more detail about the related work regarding the physiological data. And you can see some of the previous study have used different physiological data. And this is also the departure point of our research. And we basically select some more important physiological data from those previous studies. For example, the GSR, the heart rate, the EEG, and skin temperature, and so on and so on. So based on what we have described, the overall project objective is to investigate if a driver's physiological feature can help us to achieve a robust prediction of the takeover performance. For example, the heart rate, the GSR, the brainwave. But the objective of today's presentation is to provide a detailed overview of what we have done regarding the experimental design and regarding the data collection. And we also want to present some preliminary observation of the data we have collected, which will be very helpful for our further analysis of the data. So based to achieve the objective, there are a few research questions we may need to answer. The first one is that are physiological feature indicative of difference in takeover performance, either across the population or within the subject? And which of these features are generally highly correlated with takeover performance? So can those features be used to make the prediction model more robust? Another question is that what are the most appropriate way to analyze those data? And considering that those data are from different equipment and they may have different characteristics. So with this question, we start our project, and this is the timeline of our project. At the beginning of March last year, we start our experimental design, and we start to select the physiological parameter we want to use. And by July, we have start our driving simulation development, and we try to test some physiological sensors. And from July to September, we did our first dry run of the experiment, and we coordinate with our industrial partner, ASM. But during this period, is in summer, due to the COVID-19, we got a significant delay of the IRB approval, and we got some restriction from the travel. So we finalized our IRB review and finalized our experimental design by the December last year. And this year, during January and February, we did the second dry run, and we did our data collection finally. And so far, we are still doing some data pre-process and some preliminary data analysis for our data. So let me start with the experimental design and show you what we have done regarding the project. And if you see the figure at the right side, this is the equipment we use to do the driving simulation. And you can see we get different components here. You can adjust the seat, the steering wheel, and pedal, and it has 3 monitors. And there is also one button we designed to allow the subject to press and so that the simulation can go back to autonomous mode again. And inside of the simulation, we have developed different scenario. For example, we have designed different traffic density. For the low traffic density, it has approximately 40 vehicles per mile. And for high, it has 80 vehicles per mile. And we also have 3 different takeover events. For example, the obstacle in front of the car and the police by side. And also we want to simulate what if the car has some error and give the alert, but there is actually nothing happen, which means there is a fake alert. So we also want to simulate that. And if you only look at the text, maybe a bit abstract. So let me show you some screen capture of the program we have developed. So this 3 figure shows you a different scenario we have been done. For the first one, you can see within the yellow circle, there is a construction site, or you can see an obstacle in front of the vehicle, so that you need to avoid the collision. And as you can see here, the traffic density is relatively low. And for the second figure, you can see there's a police car on the side, and you may want to do something else as based on your own experience. And for the third one, you can see actually nothing happened, but the subject will still give an alert, meaning it's more like a fake alert, but you still get some warning. This one is to simulate the error in the autonomous vehicle. And this is inside of the simulation. And outside of that, we also have different different type of secondary tasks, meaning observing 1 back and 2 back. And if you see this flash, 1 back and 2 back are so-called N back is a very general secondary task to for similar studies. In short, it's just there are different stimulus. For example, the position of this box, and the subject just required to decide whether the stimulus is the same as N times before. So 1 back and 2 back here is to simulate the different difficulty of the secondary task. And those are for the experimental design. Outside of this, we have, you can see we have 3 different type of takeover events, 3 different type of secondary tasks, and 2 different traffic densities. So you can imagine we got 18 different combination of these 3 categories. So for one session, we will have 2 minutes for the subject to perform the secondary task first. And while they are waiting for the alert, and then we will give an alert to the subject, and they are required to take over the car and avoid any collision. And after they did that successfully for make the car go back to autonomous mode, they need to answer some survey. So you can see here we got 18 combinations. That's why for each subject, we got 18 scenarios for them to do. And here we have mixed, or we have randomized the sequence of different scenarios to avoid any learning curve of the subject. And in between of the simulation, we got a minutes break to set up the EEG headset and to let the subject to have rest. But before the real experiment, we got 10 minutes to set up the device, and we got 9 minutes for the subject to practice and to get used to the simulator we got. Maybe they are not familiar with the simulation we are using, so we have 9 minutes for them to get used to this program. And these are for the experimental design of the simulation. And outside of the screen, we are also collecting the physiological data. If you see these 2 figures, you can see we put the EEG headset on top of the head of the subject. And we also collect the GSR and the skin temperature from the subject from the hand. And we also, on the other side, we also have an ear clip to collect the heart rate. And we also have another set of GSR to collect the signal from different positions of the body. And we also set 2 cameras to check the feet, hand, and the face position and movement of the subject. And you can see, for example, here the subject is doing a secondary task on a tablet. And this could be one bag or could be a two bag. And here she's just waiting for the alert to perform the takeover. Once she hears the alert, she will drop the secondary task and will start to take over. So once, so this is what is outside of this. And let me show you some video clip regarding the simulation we got. The first one, it shows a good takeover performance, meaning you can see the driver successfully take over the car and go back to the right lane again. And you can see the car become green, meaning the car is ready to go back to autonomous mode again. But for the another one, I'm going to show you what is a bad takeover performance or what a failure case. So if you see here, there is still an alert, and if you see at the right left mirror, there's a car behind this. Oh, you hear something, and this is a collision. It means this subject failed to take over the car, and means this scenario is a failure scenario. So obviously, this will be a bad takeover performance. But later, we may not only focus on the failure or success. For example, if the subject suddenly press the pedal or suddenly brake, it might also be categorized as a bad takeover performance. And after they have finished this takeover performance, they need to fulfill the questionnaire as shown here. It has 6 questions for every questionnaire. And it's mainly about like how you feel about the takeover scenario, like how you engaged in the secondary task and how you perceived the performance, something like that. And as you can see, we have 18 scenarios for each subject. So it means the total number of the questionnaire for each subject will be 18, right? And here is more detail of the experiment. We did the experiment during the January and the February in CUICA. And if you see the subject demographic information, we got 20 subjects. And their age and their driving experience varies a lot. And now let me show you some detail about the collected data. So theoretically, the total data points will be 360, which is 20 times 18 scenario. And the data we used in our preliminary analysis is about 286 from 16 subjects. And we mainly get 2 different categories of data. The first is the you can so-called the input data or experimental design data. It includes the takeover events, the traffic density, and the secondary tasks. And then for each of them, we have some corresponding output data, meaning the vehicle data, the EEG data, the skin data, heart rate, and we also got the video and the survey data. And for vehicle data is a text file. It includes different things. For example, the takeover result, as I show you in the example, it can be a successful or failure. And there are also something like maximum steering, maximum acceleration. And for today's presentation, I will mainly show some results for the vehicle data and the EEG data, because as I mentioned, for previous study, they lack the knowledge of the mental status. So we want to focus on EEG data for now. And this is this flowchart shows you how we analyze the data and what has been done. We have collected the data and we have manually digitalized all the results from the questionnaire. And for some, for most of the physiological data and the experimental design data, we need some pre-process, meaning we need to clean all those raw data from different equipment. And because they are collected from different sources, like the vehicle or the sensor or even the experimental design, so we integrate and synchronize all this raw data into a single file. And for some specific data, like the EEG data, because it's very sensitive, so even eye blinking or muscle movement can cause some noise, meaning we need to denoise all this noise. So it needs some actual effort to remove the noise from the EEG data. So we also did that. And based on those clean up data, we did some initial plot and did some preliminary data observation, which I will show you later. And based on this, we will go further and further analyze all the data we collected and try to establish the takeover performance prediction model. So this is some detail of the collected vehicle data. It's exported from the driving simulator. And this is a text file, what we got. And if you open this text file, you can see many different lines. For example, here is a screenshot of what inside this text file. And on top of this, you can see it includes some general takeover information like the scenario, for example, the takeover density, the secondary tasks, the takeover events, and it also tell you the time of the takeover, when the takeover happened, when the alert happened. And we also got some other lines for different categories of raw vehicle data, like time to collision. The time to collision means the time for the car to crash if it maintains the current speed, and also the acceleration and the speed of the car, and so on. So we need to extract all those raw data into a file and synchronize all of them with the scenario we got and with the physiological data we got. And this is a vehicle data. And let me give you more detail about also the EEG data. So what is the EEG data? It's mainly some brain activity in different regions of human brain. And a common way to measure all those data is using electroencephalogram, which we in short term is so-called EEG. And there are two main features we want to focus in this study. One is mental workload, meaning the mental resources devoted to tasks of an individual, and also the work engagement, which is by definition the positive, fulfilling work-related state characterized by vigor, dedication, and absorption. And how can we get the mental workload and the work engagement from the raw data of the EEG headset? Based on the previous study, they find some pattern correlated to different the change of signal in different regions. For example, if you look at the right figure, it's a cartoon human brain, and it contains different regions. There are two important regions we are going to focus on. One is parietal lobe and one is frontal lobe. And for the signal from all this region, they can be categorized into alpha, beta, to gamma, something like that, based on the frequency they got. And we got the signal and we know the frequency. So based on previous literature, the increase of the mental workload is associated with the increasing of frontal theta activity and the decreasing of parietal alpha activity. And similarly for the engagement, it is associated with the frontal asymmetry index. And I'm going to show you in more detail how we really can get this number of this mental workload and the frontal asymmetry index, or we call the FAI. This is a general flow chart to show you how we can calculate the data from how we calculate the mental workload and the frontal asymmetry index from the raw EEG data. And there are two equations to show you the correlation of signal in different brain positions to calculate the frontal asymmetry index and the mental workload. As you can see, F3, F4 is correlated to frontal asymmetry index, and the mental workload is correlated to 4 channels. And to get the band power, we need to pre-process all those raw data for us. For example, we need to get the raw data. We need to do the offset removal and denoise it, and then get the fast Fourier transform. And I will show you more detail regarding this flowchart in next page. So the first step, for the raw data, you can see for the left screenshot, it shows you the raw data collected from the EEG headset. And you can see the number is very huge. It's more than 4,000 because it contains some DC offset. So what we need to do first is we need to remove all those DC offset, and then we can get some cleaner data like this. The number is significantly reduced. However, this data still contains a noise. We didn't actually do the noise removal. even we do the BC offset removal. So how we can do the noise of the data? Here in our study, we use the EEG lab. The mechanism is that at first we perform the independent component analysis, meaning ICA, to get sub-components of the brain signal. If you see this plot, it shows you 14 different components, sub-components of the brain signal. And it also shows you the percentage of this element to be either a brain wave or either a noise from the eye or either other unknown signal, maybe some movement of the body. So here, for example, for this one, if you can see it, there's one channel 6. It has more than 80% of chance to be other, meaning it's very likely to be a noise. So we need to remove this channel manually. So this process is a bit subjective, and people need to manually select the element they want to remove. And after we do the remove of those elements, we can get the final denoise data like this. And you can see the number change a bit. And once we got this file, we can do the fast Fourier transform and calculate the band power. So this band power will be used in the previous slides in the equation so that we can get the work engagement and the frontal assemblage index. So here we use 1 second as a time window. It means for each second, we got 1 data point for mental workload or frontal assemblage index or FAI. And this is how the frontal assemblage index looks like, and it's similar to mental workload during the whole experiment. And you can see the data fluctuate a lot. It means it's very sensitive. And you can see there are many couples of vertical dash line, and those dash line is what I use to mark the takeover period. And for the first 3 scenario marked as black, those are 3 practice scenario. As I mentioned, this is for the subject to get used to the driving simulator and get more familiar with the scenarios. And followed by 18 experimental scenario, as I introduced previously. And if you enlarge those part, you will find there are 2 lines. So the first line will be the time when there is an alert. And the second dash line is when the car go back to the autonomous mode again. And in addition, as we are going to predict the takeover performance, so it's important that the data is before the takeover happened. So that's why we calculate the average value before the takeover happened. It means for each of the subject, we have 18 data points for either mental workload and the frontal assemblage index. And then we plot all this raw data as per different subjects. And you can see here we got 2 figures. One is for FAI, one is for mental workload. And if you look at this in general pattern, you will find the result actually vary a lot across individuals. For each bar here, there are 18 points from 18 scenario. And you can see the range vary a lot across all the subjects. So we also did the standardization for those raw data and try to see how those data distribute from each other and how the results differ across all the subjects as our initial observation. And this is potentially give us some insight regarding further data analysis of this project. And we also did another type of plot. This is a data visualization guideline before I go to the real plot. And here you can see we got a plot of different dots there, and we use different line to lay out the mean of the data in 2 directions. One is for vehicle data, another one is for standardized EEG data, which can be FAI or can be mental workload. And we also get the red dashed line to mark the value that 1 standard deviation deviate from the mean, and also the yellow line to mark the 2 standard deviation away from the mean. So let me show you some of the example of the real data we plotted. This is more like a final data we got, and you can see here I plot the vehicle data, including maximum steering, maximum deceleration, and the reaction time as per the standardized FAI. And here I also label the percentage of data within one standard deviation or within two standard deviation region. And you can see most of the data, they are concentrated within two standard deviation across two directions. And about half of them concentrate within one standard deviation. And for these three plots, I use different color to label out the different secondary tasks. And like it also has different shapes to make a clear idea about whether the secondary task will cause any difference. And similarly, we changed the plot as per the takeover events. And here you will find there are some difference. For example, for the maximum steering, you will find that there is a bunch of data that it's in general lower and more concentrated. This is for the fake alert. It is normal, it is reasonable because for the fake alert, actually the subjects does not require to turn the steering a lot because they just need to maintain the speeder and the direction of the car. And another interesting observation here is for maximum deceleration. You can see a clear separation of two sets of data. And on the top of that, they are more concentrated within -10. The minus means the deceleration. And there's another group of data below the average line. So this can be a potential good indicator of bad takeover performance, meaning this group of data might be a good criteria for us to decide whether the takeover performance is good or bad. And for the reaction time, you can see it's much more concentrated than steering and the deceleration. It might indicate that the reaction time is more close for each other. And similarly, we also try to divide those plots into high traffic density and low traffic density. And if you look at the percentage of this data, you can see that it actually does the distribution of the data in from our experiment does not actually change a lot as per the traffic density. So it might indicate the data collected in this experiment has less effect of the vehicle data as per EEG data. And those are for the frontal assumption index or FAI. We also did some similar plot for the mental workload. And this is a similar plot as I showed you previously. And you can see similarly, most of data concentrate within two standard deviation region, and half of them concentrate within one standard deviation. And yeah, for the reaction time, you can see more than 80% of the data point concentrate within one standard deviation, meaning this one may have less variation, and it may give us some insight in our later data analysis. Maybe we can put less focus on a specific type of data. And we also did a for different color as per the takeover events. And you can see a similar pattern we find in the frontal assumption index. For example, the maximum steering data for the fake alert is in general lower and more concentrated. And for deceleration, it has to separate data set. And similarly, we also have high traffic density and low traffic density for the mental workload. As if you compare the percentage here, they are slightly different, but in general, there is still no significant difference. It means the driver performance and the mental workload data distribution does not actually change a lot at what we collected. So this may be a bit more a bit objective for you to summarize all the findings. So we got a page to summarize all the preliminary observation we obtained, and based on those, we can have a better analysis of the data in our future study. So at first, the physiological response, mainly the mental status we mentioned, like the frontal asymmetry index and the mental workload, to different takeover scenario and the secondary tasks vary a lot across individuals. So this finding actually supports our initial objective, which means we may want to focus on the personalized prediction model, because you can see those data are actually vary a lot across different subjects. And most of those data are concentrated within 2 standard deviation, and half of them are like concentrated within 1 standard deviation. And some type of the type of secondary task does not seem to have a significant effect on the raw data we collected when we plot versus the EEG data. And takeover events, for example, the maximum steering of the vehicle might affect by the takeover might be affected by the takeover performance. So it means it might be a good indicator, good input feature for us to establish the prediction model in our future study. And some specific vehicle data, such as maximum deceleration, might be a good indicator of the takeover performance, because you can see from the previous figure, there are 2 separate categories, group of the data, and we may use those as criteria to decide our good performance or bad performance. So those figures indicate the underlying relationship between the EEG data and the takeover performance. So further data analysis is necessary to establish all those relationships. So this will be part of what we are going to do. And the subsequent data analysis of the remaining physiological data, as I mentioned, the GSR, the heart rate, and the skin temperature, can maybe provide further insight regarding the secondary task and takeover performance on and the takeover scenario on the takeover performance. So based on all those preliminary observations, we have decided, and we are currently doing some ongoing work. And what we are going to do is that we will understand the relationship between the physiological data, mainly including EEG, GSR, and heart rate, and then the vehicle data, and with the final takeover performance. And based on those relationships, we will select some of the important features, and we will try to establish maybe both the personal prediction model and the general prediction model for takeover performance. And we will try different algorithms. Maybe we can try the conventional algorithm like random forest, and because the physiological data is time sequential data, so we will also try more advanced time sequential algorithm such as LSTM. So this is what we are going to do in the future, and what we have done in the past year. Here I want to acknowledge the financial support from the CCAT, and I also want to acknowledge the support from CUICA and the ACN. These are some references we used in this presentation, and thanks for all your attention. If you have any question, we are out here to answer your questions. Thank you.
And the first one is, you propose to use personalized models to account for interperson variation. Have you established that behavior of an individual is consistent over extended time and across multiple sessions?
Currently, we did some preliminary data analysis for the data we collected, and for the count time, we only got around 1.5 an hour. We got 18 data points. So that's why we plot all those data and see how it looks like. So in later part of this project, we may try to see whether the time will affect the final result, and we may try to get more data, and we may spend more time on individual subject to get more data. in that way, we can establish a better personalized prediction model. Yeah, maybe Professor Menassa have something to add.
Thanks, Min. No, I think just to answer this question, for this study, we have 18 scenarios per subject where we varied like the traffic density and the driving takeover scenarios. But to establish physiological models for the subjects, eventually we would need to have basically revise our experiments based on the results that we have and collect additional data to be able to support this.
Excellent. Thank you so much. So this next question, I think, is more pointed towards the future work on this project. Given that drivers won't wear any of these sensors, I think they mean in the real world, how do you propose approaching this in a vehicle if this research moves there?
So we are going to maybe revise, maybe add more experiment to this counter progress, and we may design different scenario. And we are going to collect more data because currently, based on the initial observation, we already have some insight about how those data distributed. So this gives us more thinking about how we can finally because currently there's still no very clear criteria for bad or good takeover performance, right? So by observing all those raw data we currently have, we can establish a better sense of how we can decide the bad and good takeover performance. And then based on the data we collected, the physiological data, and we will try to select some more important feature as also based on those plot, and then we can try different algorithm and see how it performs.
So Kelvin, can I add just one thing to this question? So it's true that in a realistic scenario, like in a realistic driving scenario, the driver is not expected to be wearing all these types of sensors. So one idea that our group is exploring is to look at how some of the common physiological features, so for example, heart rate, which is typically monitored by any wearable watch you might be wearing in the car, can it be used as a proxy for some of the more, if you want, difficult to collect physiological data? So as part of our subsequent research as a team, this is something we are interested in as well.
Great, thank you. This next question is, have you considered an EEG algorithm for cognitive load? This would provide significant data regarding TOP.
Actually, for the EEG data, there are already many previous studies that highlight different feature we can use. For example, the mental workload we used and the bundle assumption index we used. Currently, we are just using some existing, and those has been existing features. Those have been proved in many literature. So it's it could be a more standardized way to do that. And in our future work, we might incorporate more features that we can obtain from the EEG data, like the overall band power or like a more advanced algorithm to deal with the EEG. But currently, we may just want to see whether we can find something regarding the mental workload and the work engagement first, and we will decide.
Excellent. This next question is, assuming the driver is in fact not sober or is medically impaired, how do you anticipate the physiological sensing controls to respond?
Yeah, like it is hard to say whether like the difference can be tell from the real experimental design or the physiological data. So that's why we plot our initial data, and we see which really cause some difference. For example, physiological data may be more sensitive than the real road scenario. For specific type of physiological data like heart rate, like the GSR, maybe one of them will be more sensitive and more indicative than the other. So that's another reason why we did the in preliminary observation, so that we can have a better insight of what final feature we want to use in regarding the establishment of the prediction model.
This next question is there any guess or science to how the number of practice sessions may affect takeover performance? Average vehicle ownership is roughly 7 years. Will that driving experience improve or degrade takeover performance?
Oh yeah, that's a very good question. In our counter analysis, we just mix all the data and we try to get the data from different subjects with different experience. But this is also an interesting topic, and to avoid the difference regarding the driving experience, so that's why we set a practice period for them to at least get used to the simulation. But eventually, because the autonomous driving car is designed to everyone, regardless how many years they have been driving. So that's the initial idea of this experiment, and that's why we haven't yet separated them. But in the future, there may be a pattern to see, for example, for the more experienced driver, they may be more used to this type of design. That's also maybe can be a part of why we claim as personalized takeover performance or personalized alert for different subjects. And it's kind of aligned with our objective, I think.
Excellent. This next question, I get it's more of a comment. A potential future work may be to see effects of event intervals on those measurements. Events happen every 3 minutes in this study. If we do it at every 5 minutes or every 10 minutes, data may be different. If it is different, it suggests we need to remind drivers every 3 minutes, 5 minutes, or 10 minutes during their L3 driving. Any thoughts on that?
Actually, the purpose of this experiment is not like to give a fixed time of the alert. It's the main idea behind that is we are going to predict the takeover performance, expected takeover performance of the subject. And if we detect that the subject is not engaged, it might have a bad takeover performance. If we give the alert now, they may fail to take over. So in this case, we will give an alert to remind that, okay, you are now not ready for the takeover performance. That's might not be a fixed time. For example, the subject may be fully ready for the takeover for a whole hour, but for another period of time, they may be more like not ready for the takeover for each 2 or 3 minutes. So this one is not something that we want to fix, but something we want to decide by the predicted result of the takeover performance.
So, Carol, if you allow me to just add on this, I think this is an important question in terms of how, because the takeover, or at least we are hypothesizing that the takeover will be affected by how engaged the driver is with the secondary task. In our experiment, most of the driving scenarios we used were 3 minutes, but we expect that as the time increases, so we go up to 5 minutes or 10 minutes, the individual engagement with the secondary task might increase, and it might have an effect on the takeover performance. I think the question and the potential future research in this area is important to explore the effect of time on the level of engagement of the driver with the secondary task they are doing.
Thank you. We just have a few more questions here. So if you have any, get them into the Q&A or chat box. So in addition to feasibility of physiological sensors for predicting driver response, can the study draw any conclusions regarding human ability to take over reliably and safely, essentially the ODD for the human?
Yeah, I think in the future work, we will also consider the human difference. That's also what we emphasize a few times. Something like this should be personalized. So for different person, they may have different ability to take over some, to handle some emergencies. And regard of the physiological data, we in the future work, we may consider like the human characteristic as also an input feature of the prediction model. For example, the driving experience and the age and something like that. I think potentially those may also, we will see whether it can potentially improve the accuracy of the prediction model.
Excellent. Okay, we have one more. So this kind of gets into the simulator versus the vehicle on the road. So they want to know, how do you link the physiological signatures with driver monitoring from onboard cameras in L3 to develop surrogate measures for driver readiness?
Currently, we got some camera to capture all the scenarios, and we got a signal from the vehicle. We manually mark all the takeover period, and we can synchronize them from the video we obtain on the screen recording we obtain. But eventually, as we mentioned, we have a industrial partner, Asian. We got some equipment that can link all these things and synchronize all of them together. So if we find something and we can successfully establish the prediction model, we can incorporate all this and integrate all the hardware together to a car or to a simulator. So that can be achieved.
Okay, great. Thank you so much.